Yeah, anyway, we will look at, we will have a demonstration later, but I will just give you one example case results. What is presented in this slide is equilibrium composition for kerosene air mixtures. Kerosene is taken to be, for example, this is one case where you can use the enthalpy of combustion to back calculate the formation enthalpy. Okay, so what is done here is exactly that. So kerosene is a mixture of a large number of hydrocarbons. We the approximate formula for that is what is given here, is CH2, okay, and the enthalpy of formation is back calculated from the combustion enthalpy, and air is also taken to be an equivalent composition with a certain amount of oxygen, nitrogen and carbon. Remember that you can, you are allowed to do all of these things because all you need to make sure is that the energy bookkeeping is done correctly. Okay, you can express the composition in any form. It does not have to be H2O, or it does not have to be, kerosene need not be considered to be precisely the mixture that it is made up of, as long as you get the carbon and the hydrogen correctly. Okay, and the pressure is taken to be 1 bar. Yeah, what is done here is for a variety of air to fuel ratio, temperatures, flame temperature, adiabatic flame temperature is calculated, and also the post flame gas composition is calculated. The important things to note are we go from an air to fuel ratio of 10 to about 30, stoichiometry is around 15. Okay, so on the left of 15 the two cases are fuel rich, and to the right of the stoichiometric cases the two cases are fuel lean. Okay, so the equivalence ratio is greater than 1 on the left hand side and less than 1 on the right hand side. It is about 1 in the for the case in the center, okay, the third case. What I want you to notice is for this case the temperature, the adiabatic flame temperature drops on either side of the stoichiometry. Okay, it is about 2270 kelvins at stoichiometry, and it drops off on either side, and of course correspondingly you can see that the composition is also consistent with it. There is no oxygen, there is no leftover oxygen when the combustion is rich. There is some oxygen left over at stoichiometric, because remember that the products are at very high temperatures and therefore dissociation will happen. So carbon dioxide will dissociate into carbon monoxide and oxygen, and water vapor can dissociate into hydrogen and oxygen. Therefore there is a little bit of oxygen that is present at stoichiometry. Of course the excess oxygen in under lean conditions also can be seen here. Okay. Well, other thing to note is, of course, on the fuel rich side you have fuel species that are left over, hydrogen, atomic hydrogen, molecular hydrogen, carbon monoxide are present in the fuel rich side, but the moment you go to the fuel lean side the hydrogen disappears, the carbon monoxide concentration is much lower. Recall the NOx versus carbon monoxide and its relation to equivalence ratio. This is the simplest way to understand it. Okay. Well, you also see other things, the relevance of which we will see later. The molecular weight is given, the gamma is given. These are relevant for rocket calculations, and we will see these aspects, discuss these aspects later. But what I would like to discuss now is I posed a question here, why a mixture of kerosene air at 1 atmosphere and 300 kelvins not at equilibrium state? What I mean by that question is, if I start with my initial condition is a stoichiometric mixture of kerosene and air at room temperature and room pressure, you input this data into NASA CEA code and say calculate, you will get this answer. You will get a temperature of 2266 kelvins and composition corresponding to this. But the reason why I am posing this question is this is not consistent with our common sense experience. When you prepare this mixture, for example in this room, okay, and wait for it to spontaneously get converted into high temperature products, it does not happen. So what is it that we are missing in the equilibrium calculation? Okay, one answer is that these things happen at a finite rate, and so they will not convert spontaneously. Okay, so the that is a correct point, that the rate at 300 kelvins and 1 atmospheres is so small that there is no significant product formation at room temperatures. Yeah, you were saying?
requires some initial reaction happening, you need to separate.
Yeah. So since the reaction rate at room temperature is so small, you need to provide an initial kick. So if you create a small zone of high temperatures where a certain amount of product is produced, okay, where the temperature has been increased to sufficiently large values, okay, for the rate to become significant. Once a zone of that kind has been created, then the reaction proceeds very fast. Okay, we know that in a premix case, once you provide an ignition, a small flame kernel is created, and then the flame kernel propagates through the mixture, converting the reactants to products. And if you wait for a few seconds, you will have a condition that is close to equilibrium after this propagation has ceased. Okay, is that point clear? That is what I have shown in this simple diagram. What you see on the x-axis is the reaction progress. We start with reactants. The reactants are at a high free energy state and the products are at a low free energy state. So what thermodynamics tells us is that the reactants must spontaneously become products, and that is exactly what NASA CEA calculates. What is missed in the equilibrium calculation is that there is actually a high energy barrier that sort of separates the reactants from the products, and for the actual process you should provide a kick or a push that will take the reactants over this hill and make it products. Okay. So what thermodynamics or what thermodynamic equilibrium calculation sees is only this difference in delta G. Okay, it does not see the activation energy associated with the activation barrier. Okay. So well, this we have already seen. For a reaction to be exothermic, the energy required for breaking the bonds must be less than the energy required for the formation of the bond, so that the net reaction is exothermic, and the bond breaking is endothermic. The reactants to convert to products, the reactant molecules must go over an energy barrier, okay, or a transient state as it is called. It is because the bond breaking process is endothermic, and the probability of when you have created a mixture of this kind, the probability that a collision is energetic enough to create sufficient number of transient state radicals or transient state molecules is proportional to exponential minus EA by RT, the Arrhenius function. So the rate is controlled by exponential minus EA by RT, which is this energy barrier, but equilibrium concerns itself only with this delta G. As long as this delta G is negative, it converts the reactants to products spontaneously. I just want to mention that so you need ignition systems to cross this energy barrier, but we also have hypergolic combinations. Okay. So what happens in hypergolic combinations is that when the fuel and the oxidizer are brought into contact, there are certain energetic condensed phase reactions that can start immediately. They have zero activation energy, and those reactions can start spontaneously, raising the temperature for the rest of the oxidizer and fuel to get converted into products. So the hypergolic combinations do not require ignition because of that, yeah. But every other combination requires ignition. Again, more cases here. What is shown is two things are shown. One is effect of initial temperature and also effect of initial pressure. Okay, let's okay, I can't see a case where the pressure is 1 bar and the initial temperature is 600. Okay, let's not worry about it. Let's look at these two cases. Methane air, the pressure is for both these cases is 20 bar, 2 megapascals. Here the initial temperature is 300, here the initial temperature is 600. Of course, the enthalpy that is used to raise the temperature of the initial reactant is available for raising the temperature of the products also. So some of this gets reflected in the final temperature increase. Okay, and well, of course, the same thing is shown for methane oxygen combination also. I don't want to discuss it in detail. The point that I want to make is that, of course, raising the temperature of the reactants will increase the adiabatic flame temperature. The other point which I want you to think about is at the same initial temperature, increasing the pressure will increase the final adiabatic temperature till some level of pressure. Okay, that is because the extent of dissociation decreases with increase in pressure. Just again, few more cases of equilibrium composition. This is for Okay, this I wanted to include because I made a point here saying that the temperature is maximum at stoichiometric conditions. This need not always be the case. One example is oxygen hydrogen system, where maximum temperature occurs at rich conditions, sufficiently rich conditions. Okay. Again, one more case of hypergolic combination of propellants, nitrogen tetroxide and unsymmetrical dimethyl hydrazine. These are just I wanted to show the trends in flame temperature, molecular weight, and what is called the characteristic velocity, which we will discuss later. Right now I will suggest that you look only at the way flame temperature changes with the oxidizer to fuel ratio. Okay. In different communities look at measures of oxidizer to fuel ratio in different ways. In combustion literature it is usually equivalence ratio, but if you talk to a liquid propellant rocket person, he will talk about mixture ratio. Okay. And if you talk to a solid propellant man, he will say solid loading or the amount of AP that is present in the propellant. Okay. But they are all essentially the same measure, you can calculate one from the other. Okay. Yeah, so this we have already discussed. I will just formalize the notion of reaction rate and Arrhenius parameters. So we saw earlier that equilibrium is controlled only by the difference in Gibbs free energy between the reactant and product states. If the difference is negative, that products have a lower Gibbs free energy than the reactants, the reaction is taken to occur spontaneously and the equilibrium state is achieved. But in reality there is an activation barrier to cross this, and this requires a kick in the form of ignition, and because of the activation barrier the reaction rates at room temperature are negligible. What you see here is a plot of reaction rate versus temperature. The reaction rate is almost 0 at low temperatures, and it becomes significant only at a certain temperature, and that temperature depends on what fuel oxidizer mixture you are dealing with. Okay. Therefore, the reaction rate exponentially increases with temperature. So, once you cross a threshold temperature, the reaction rate increases exponentially, but also remember that in the process the reactants are consumed. So, the reaction rate is proportional to the concentration of the product of the concentration of the reactants and a temperature function, which is the Arrhenius function. So, as the temperature increases, this term, the exponential term, will go up very fast, but in the process you are also consuming the reactants, and therefore at some point you will reach a stage where all the reactants are consumed and the reaction rate will drop to 0. Okay. So, this state is close to the equilibrium state when all the reactants have been consumed, converted into products, temperature is increased and an equilibrium state has been achieved, and the reaction rate goes to 0 at equilibrium state. Okay. The net reaction rate goes to 0 at equilibrium state. Well, any questions at this point before I get started with this? I think I have a couple of slides before we close this lecture and move on to the NASA CEA demonstration, but if you have a question I can answer now.
How does the initial pressure increases the stoichiometric adiabatic flame temperature?
Sorry? How the initial pressure increases. So, the extent of dissociation, for example, if you consider the dissociation of carbon dioxide, if you fix the temperature at let us say at 2000 kelvins, okay, at 1 atmosphere the extent of dissociation of carbon dioxide will be much more than what it is at 5 atmospheres, and the dissociation reactions are endothermic, so they will consume energy and bring down the temperature. So, once the extent of dissociation decreases as the pressure increases, the flame temperature increases. What I want you to think about is why does the extent of dissociation decrease with increase in pressure. That is something that I will leave it as an exercise for you to think about. Yeah. Any other questions? Yeah. No? Shall we move on? Yeah.
Can you go a couple of slides back?
Yeah, sure.
This, why it is plotted against N2O4 by UDMH?
Yeah, that's what I, so if you, in the liquid rocket propellant literature, the variable that is used to, specify the fuel oxidizer ratio is what is called the mixture ratio. It is the mass flow rate of the oxidizer divided by the mass flow rate of the fuel. So here this is a hypergolic combination where the oxidizer is nitrogen N2O4 and the fuel is actually UDMH, unsymmetrical dimethyl hydrazine. So this is the oxidizer, this is the fuel. So the way the equivalence ratio is expressed is as the ratio of mass of the oxidizer to the mass of the fuel. So this is the ratio of mass of the oxidizer to the mass of the fuel. Yeah. Any other questions? Okay, I will just spend about 10 minutes discussing this. We have discussed equilibrium, but we have also seen that there are some aspects of combustion which are dependent on the rate of the chemical reactions. Okay, so when looking or when analyzing flames, it is important to identify the dominant process. Sometimes the dominant process is mixing and equilibration, sometimes the dominant process is chemical reaction. Okay. So what I am referring to as equilibrium versus rate control processes is equilibrium refers to processes where the chemical reaction rates can be considered to be much higher than every other process. Okay. So there is sufficient time available for the reactions to go to equilibrium. Okay. So the rate of those processes are not controlled by chemical reaction rates because the chemical reaction rates are much larger than the other processes. It will be controlled by the slowest of all the processes that happen. Okay. One example of such a case is what is shown here. What you see here is an ethanol droplet suspended by a quartz rod ignited with a spark. You can see a thin bluish color flame that is surrounding the droplet. It is not prominently visible because the picture has been taken with backlight so that you can simultaneously see the flame as well as the droplet. So in the absence of the backlight, you will actually see a prominent blue flame here. Okay. This flame is formed by the reaction between ethanol vapors that are coming off from the surface of the droplet, which come off, mix with the air from the surrounding and react and form a flame. So this is a non-premixed situation, this is not a premixed situation. This is a non-premixed situation where ethanol vapors come from inside of the flame, oxidizer diffuses from outside of the flame, both diffuse towards the flame, mix and react. In fact, they move towards each other, mix and react, and the point of maximum reaction is the flame. Okay. So here is an example where for instance this process or the time it would take for the droplet to completely vaporize is what controls the process here. So the limiting time scale is the droplet vaporization rate and not the rate of chemical reaction. Okay. So this is a case where if you for example assume that the reaction rate is controlling, the time scales that you would estimate will be much smaller than what in reality it is. Okay. So what happens here is, since the reaction rates are much higher, the vapors of ethanol and oxygen from the surrounding air have a lot of time to equilibrate. Okay. So the reaction rates are much larger, so there is a lot of time available for the reactions to go to completion, go to a point where the reaction rate or the net reaction rate is 0. Okay. So in fact the state around the flame will be close to what you see here. The temperature will be close to the adiabatic flame temperature and the reaction rate will be 0. That is, these observations are what are summarized here. I will go through it just to make sure that I have conveyed all the points. I conveniently chose a premix flame where the reaction rate is controlling to calculate the length scales to justify the continuum assumption and the assumption of thermodynamic equilibrium. So while calculating length and time scales of relevance to premix flames, we use the reaction time as a limiting time. Okay, I picked an example where the reaction time is a limiting time. That is, we implicitly assume that the process is rate controlled and equilibrium is achieved towards the edge of the flame on the side of the products. Okay. But of course there are a lot of cases in reality where the reactants are not premixed. For example, the droplet flame that you see on the right. In these cases the time for mixing can be the limiting time and the reaction time will be much smaller. In fact, in this case the time for mixing is also not the limiting time, it is the evaporation time that is the limiting time. Therefore, most of the reactions will occur in a very thin zone. It is not that easy to define a thickness here. If the reactions are infinitely fast, the reaction zone is necessarily has a thickness of 0. Okay. So, therefore, most of the reactions will occur in a very thin zone where the fuel and oxidizer are mixed in stoichiometric proportion. So, the flame will essentially separate the fuel from the oxidizer. In the premixed case, the flame separated the reactants from the products, the premix reactants from the products. Here it separates the fuel from the oxidizer, and the conditions at the interface will be close to equilibrium. The rate of transport of fuel and oxidizer to the flame is much slower than the chemical rate of consumption of the fuel and oxidizer, and hence the conditions estimated from the assumption of thermodynamic equilibrium will match conditions at the flame. So, you can, as far as the chemical state is concerned and the as far as the thermodynamic state is concerned, you can assume equilibrium. What you need to accurately account for is the time it takes for the mixing of the reactants to happen, or mixing of the fuel with the oxidizer to happen. So, the rate of burning is limited by the evaporation rate of the droplet for the example that is shown here. The rate of chemical reaction here will be much larger than the rate of evaporation as well as the rate of mixing of ethanol vapor with air. Therefore, the conditions, I am just repeating this point, the conditions in the flame zone will be closer to equilibrium. For instance, the flame temperature will correspond to the adiabatic flame temperature. Okay. I think I will stop here. I have spoken for about an hour. I will take some questions if you have. Yeah. Yes, sir.
You showed an equation for reaction rate, sir.
Yeah.
How will it mix up? Are we going to find it T8 billion?
We will discuss that when in the next lecture. It is difficult to measure reaction rates, but there are simple ways by which we can get an estimate of the overall or the order of the reaction rate by quantities that are easier to measure compared to reaction rate. For example, I showed an equation for the reaction rate which I use for calculating the look at this equation. Omega dot goes as Cp over K rho u Su squared. So, omega dot is a measure of sort of an average reaction rate over the flame thickness, which is not easy to measure. But what is easy to measure is the flame speed. So, once you know the flame speed, you can relate it to the reaction and the reactivity. You will not get the exact magnitudes, you will not get information about all the complicated pathways through which the actual conversion of the reactants to products happen, but there are situations where that information is not required. For example, there are situations which one example of which is the combustion process that happens over the surface of a composite solid propellant. This kind of strategy or this strategy for estimating reaction rates from flame speeds, the numbers that you get are good enough to actually create a theoretical framework for calculating or predicting the burn rate of composite solid propellants. Okay. There are a large number of parameters involved. All that you need to make sure is that the set of parameters are internally consistent. Once you ensure that the predictions match with the experimental results. But the reaction rate is only an average reaction rate estimated from a relationship of this type. We will discuss this in some detail later today and tomorrow in the context of solid propellants. Any other questions? Yeah.
You told like magnesium and aluminium is also used as fuel.
Yes.
So how we use these as a fuel? Like we mix with some other fuels or like?
Yeah. In the case of solid propellants, for example, if you one example is the solid rocket boosters that are used in the PSLV launch vehicle. It is called an S200 booster that has a propellant which consists of ammonium perchlorate, mixtures of ammonium perchlorate, HTPB, which is a kind of rubbery like material which acts as a hydrocarbon fuel, and aluminum. So, all these are mixed and made into a solid block which can then burn, okay. And what generally happens is the ammonium perchlorate is the oxidizer, HTPB and aluminum are fuel. So, the ammonium perchlorate and HTPB react and form combustion products, and aluminum can be oxidized by the combustion products of AP and HTPB. For example, aluminum can be oxidized by water vapor, aluminum can be oxidized by carbon dioxide also. So those exothermic reactions add more enthalpy to the hot gases that flow, and that enthalpy increase can contribute to a better performance. So the way the aluminum is incorporated into the propellant is by mixing it and making it into a solid block. And if I remember right, magnesium is used in Astra propellant, for example. So these are all mixed and made into a solid block which is burnt inside the combustion chamber.